Cool. All right. Thank you. Yeah, Richard Kiene, engineer at Joyent. Here's my talk on why I love BGP. Although I'm going to be really honest, when I started getting together the history for this, I started loving it a little less. And then I came back around, so we'll see if we can bring you guys there too. I'd be crazy if I didn't mention one of the things that got me into this industry and made me love things like BGP, Doom, if you're familiar with it, awesome. If not, it's a game from way back before you were born. But this is what gave me my desire to learn connected systems. I really love network systems. One of my earliest memories of connected systems was, punching in someone's phone number to the game and connecting to them. And that was how you did it back then. There really wasn't a good way to connect, geographically disparate systems. I mean, there was, but only the government had it, whatever. And then, this kind of compelled me to get a little further. How do we get more machines together? We cobbled together this IPX token ring setup that took us like 6 hours just so we could play Doom. And actually, it turns out that was the most fun. And then by the time we could play Doom, Mom's like, you got to shut it down. Dang it. Okay, so that's just a little bit of background on why I love connected systems. And I think that you'll appreciate, my love of BGP because of that. So BGP was primarily designed by Yakov Rector and Kirk Lougheed. You might see below kind of some important things that they've done. CIDR notation, private networks, RFC 1918, you might have heard of that. Ever seen 192.168? Yep, okay. Cisco, little company. So these guys designed this, pretty noteworthy people. If you want to look into some of the stuff they've done, I would highly recommend it. Really, really foundational things to the internet today. So in the beginning, BGP was kind of half-heartedly called the TNP, or the three napkin protocol. It was designed over lunch by these guys on 3 ketchup-stained napkins. And largely, what ended up on those napkins is what we have today. Now, there's been additions and whatnot to the protocol, but by and large, BGP hasn't changed a ton at the core since designing it over lunch. So it kind of gives you an idea of, okay, this can't be too crazy complicated. Yet a lot of people think that BGP by itself is this big, scary beast. And it can be, but not by itself. So broadly, what does BGP do? You could kind of think of BGP as a way for computers to have Google Maps to tell you how to get places. Sometimes it works just as poorly as Google Maps. Sometimes it works better. Oddly enough, Google Maps is using BGP. So why was BGP created? BGP was created to connect different supercomputing and autonomous systems. Yeah. Maybe. Uh-oh. That's all we got. Yeah. So it was a cooperative agreement for regional networks and supercomputers by NSF. And so they were trying to solve this for NSFNet Backbone Phase 2. And back then all they had was EGP, which was kind of problematic, lots of different route flapping and communication errors. EGP requires a perfect spanning tree. So you have one route, which was the DARPANet, and that goes away intermittently or whatever. You are hosed. You're always going up and down. You can't have any loops. No one else can help you out. So this really wasn't, palatable for interconnected systems that need to be on all the time. So this goes back to the napkin. They're like, okay, let's hack this up. Let's create what we need right now. They weren't interested in doing something crazy elegant or designing for 20 years out or even imagining what we have today. I think that if you listen to talks and prose that they've written, they didn't really even think that what we have today was what they had in mind. They just wanted to solve the problem they had. And they called it a hack. There's a talk by Yakov about 10 years ago, I think, and he literally calls it a hack, or if you want to be politically correct, he calls it pragmatic. Okay, this is where I start going off the rails a little bit, and I'm like, okay, this lovely thing, I used to like it. And it's evident even in how it came to be. So it starts out with a napkin, then actually what happens is just a few months after that, Cisco and IBM sit down and create working implementations of it. They're talking, they're going, and then they write the RFC. Wait, I think it works a little different than that normally, right? So very unorthodox, very YOLO. These guys, not only were they like a backwards like design process, they were shipping this thing with reckless abandon. And keep in mind, this is now a core component of everything in the internet. At this time, they're just like, rev it, keep it going, ship it, who cares? I mean, so we went from BGP 1 in 1989, BGP 2-ish in 1990, and now all of a sudden we're at version 3, just a few years later, in 1991. Now, thankfully, it took a little while longer to get to 4, and 4 is mostly what we're on today. But you kind of get the idea. These guys were sort of incrementing and almost the move fast and break things motto, which starts to get a little bit scary for systems people. So how does it help us? Let's get back to that. You type in a website, you need to know where it goes. If you understand that, all of that, great. But this is what puts you in the right path to get there. You might say it puts you in the right tube. Sorry, couldn't help myself. So as soon as packets leave your network, you're using this routing protocol. We'll get into that a little later, but basically your network being a part of an autonomous system that's a private network, when you go outside of that, BGP is helping make those decisions. So you can kind of think of it like exchanging information on how to get somewhere or what to buy in a small town. So you might want to buy some cheese. And you go to your buddy Kellen and you're like, hey, Kellen, where do I get some cheese? Do you sell that? He goes, well, I don't sell that, but you know what? Noah, he sells everything. Like, go talk to Noah. I'm pretty sure he's got it. And Noah's like, no, actually, I don't have it. But, you know, go talk to Kristen. And Kristen has cheese, I'm certain. And Kristen's like, actually, I do. I got cheese. Here you go. Buy some cheese. And BGP is pretty similar to that. It's a simple exchange of talking to people of how to get directions. So let's say you want to join the small party of BGP speakers on the internet. Like, what do you need to get into that? Well, you need an autonomous system number. So you register yourself with, like in North America, you're going to use ARIN, and you get a number that represents your private networks. It may also help represent the network that you put out to the public internet. And then so this is what's called a prefix. And these are how you learn that 9 dot whatever goes somewhere is a prefix that's being advertised. Interestingly enough, with BGP, this isn't an automatically learned process. This isn't like ARP, where you're telling someone, you know, what you have and they're asking who you have, and just as soon as you plug your network cable in, you're good to go. BGP starts with an out-of-band agreement between one or two or more people. And you actually have to kind of trust each other to some extent and work together out of band to set up the configuration and what that looks like. So it's a little bit unique when it comes to routing protocols that do a bunch of work. What does this look like? So here's a simple peering. These are completely made up examples. These AS numbers definitely exist, but they don't exist like this, I don't think, unless I got really lucky. And so let's pretend we're AS 1, 2, 3, 4, and we're going to show two depths of peering relationships. At this point, we're only peering with AS 5, 6, 7, 8. So basically, everything we know about the outside world is going to be learned from AS 5, 6, 7, 8. But AS 5, 6, 7, 8 knows 9, 1, 2, 3, 4, 5, 6, 7, and 8, 9, 1, 2. Okay, so they have their own, and this keeps piling on each other. So you can kind of see that this builds a graph. So these are some important definitions. I'm not going to rattle them all off at you, but autonomous system we've covered. Origin is you and what you originate from your network, so your IP address. The AS path is actually a calculation. It's a set or a sequence of that we defined in that last chart of basically how you might get somewhere. And then kind of I'll skip over these other ones because they're a little complicated. There's IBGP and eBGP. IBGP is a connection between internal, so private, and same AS peers. eBGP is what you do in the public internet. That's where you have, I don't know, Microsoft talking to Amazon, talking to Google. That's an eBGP generally relationship. So this is the route selection algorithm loosely. If you look at Cisco and Juniper's documentation, they kind of disagree with each other to some extent. Hopefully they kind of figure that out when they're talking to each other. I've never mixed those two. I've mixed some other interesting router types, but that's why I have emoji in there, because actually it seems like there's nothing that prevents that that you could just use about anything for your route with the local preference. We want to prefer originated routes, meaning like let's choose the route with the person that actually has that address. The shortest AS path, that's what gets us the best path to where we're going to go. That's not necessarily the geographically best path. You should understand that. You could have a cross-country BGP peering that's one hop, and that could actually be longer than a few hops nearby. But yeah, we'll skip right over that. So here's the idea in a much more complicated peering. There's a few different ways we can actually get to AS9123. You can kind of trace them yourself, but this is going to be our best path, let's say. Well, if AS6789 goes away, we no longer have that path. But what's cool is that AS5678 also knows how to get to AS9123. And we still are getting that information. We're just discarding it because we don't need it. It's faster to go through the other one. Well, here's how BGP can self-heal itself and give you a better path. Interestingly enough, when your routers are sitting there talking to other BGP peers and then collecting all this route information about where things should go, basically what they're doing is adding routes to your route table in the OS. So if you've ever done a netstash-nr on your box to see where something goes, it's really not any different on a router. And in fact, if you're running something like an OpenBSD or a FreeBSD router on the edge, it literally is this. And all that the BGP daemon is doing is inserting routes in there and removing routes from there. It's just that if you're getting a full route table, you're going to have like 512,000 of these in there. And if you only have one peer, they're all going to point to that one. So this gets what's really cool, is that when you are announcing a prefix on the internet to another BGP speaker that talks to other BGP speakers, you can influence the entire internet and how they get to you. Just this simple exchange of information cascades across all speakers. This is one of the ways that you can get geographic redundancy with your site, is that you can have BGP speakers all over the world advertising the exact same address. And so you're always going to choose the path that's closest to you, and that's not going to be the same. If you've got a server in Seattle and a server in Berlin, it's going to be a very different route if you're in Atlanta or if you're in San Francisco. Gets back to the self-healing. If you have that and Berlin goes away, well, Atlanta and San Francisco are both going to talk to the Seattle one as long as it's still there. And you can kind of see that again. I just wanted to get back to this graph so you can imagine AS1234 doesn't exist just in one geographic location. Same with the rest of them. They can be anywhere. So with that ability to influence everything, there's quite a few things that can and have gone wrong. Accidental advertisements. One of my first peerings that I set up ended up with the networking individual on the other side telling me, hey, don't advertise things that aren't yours. And I'm like, well, I'm gonna advertise only mine. He's like, yeah, well, sometimes people get the full route table and then they advertise it back to us and then we end up with this bad problem and none of our customers can talk. And it's like, wait, you're not supposed to take that from me. But anyways, that can happen. If the other side's not configured properly, you can hose them over pretty bad. And actually, like, bad things can happen if, like, tier 1 ISPs decide that, you know, a single route for really, like, I don't know, one of Google's prefixes goes through some peer that it shouldn't, and we take them down. There's things like route poisoning and over-centralized peers. This is where, like, every path is dependent on something like, oh, I don't know, layer 3. and layer 3 goes down, and half the internet is having some problems. Real story. So it's kind of the Wild West out there, which is really interesting. I love this. It's when you break it down to like its simplest form and you talking to one other server and exchanging information, it's actually a pretty simple concept. There's lots of little knobs and things that you can tune, but by itself, it's not this big scary thing. When you get to the compilation of all of it, yeah, it's totally nuts and everything is a little bit scary, but you know, that's why we have abstractions. So anyways, that's all I have. Thank you.